Learning Outcome 3.6. Calculate the exponential Fourier series coefficients of a general periodic function using the Fourier series integral. We've so far talked about how to calculate Fourier series coefficients if we have a purely trigonometric function. This learning outcome deals with a general periodic function, something that's not simple sinusoids. When we want to do that, we will use this formula, the Fourier series analysis integral. This is equation 3.39 in your text on page 191. In order to use this, we need to know about t, a0, and ak. We'll start with t. T is the period of our periodic function, the smallest distance it takes for a function to repeat itself. That will determine our value for t. We're then going to integrate over t. Usually you see a definite integral with a lower limit and an upper limit that tells you exactly where to start and stop integrating. When you just see this one variable, it means integrate over any one period. You choose start, you choose stop. So we could start here, we could stop here. We could start here and stop here. We could start here and stop here. We usually choose our period, so the mathematics of the integration and the algebra that follows will be simpler. Therefore, a preference for starting at the beginning of an object, an end of an object, or sometimes right in the middle of the object. But there's nothing saying that you couldn't pick some other arbitrary spot. It's any period you choose. They will all give you the same answer, but the mathematics might be harder to get to something that's pretty to look at. Next, we'll look at a0. This is called our DC component of our Fourier series. And this occurs when our value k is 0. In order to calculate this, we use this formula, but we substitute in k equals 0. Notice you can simplify this complex exponential, and we get 1 over t integral over any one period x of t. This integral is just the area underneath our function over the duration of one period. And because we're dividing it by capital T, it makes it the average area in that period. Or, because it's periodic forever, the average height of our function overall. So here's an example. If we pick one period and look at the area that's under it, that's going to give us the value for this integral. Divided by t, that will give us this value here, which is that average area. A sub k. This is our general Fourier series coefficient, and for this we will just use this Fourier analysis equation. So let's consider an example with this function. We need to integrate over any one period, and I have arbitrarily chosen to integrate from 0 to the end of the period, which I'm calling 3. We're therefore going to integrate from 0 to 1, where the function has an amplitude of a, plus from 1 to 3, where the function has an amplitude of 0, and that term will go to 0. We're almost done with the learning outcome. A few mathematical simplifications you're going to use occasionally. Recall that e to the j 2 pi is 1. Has a magnitude of 1 and a phase of 2 pi. E to the j 4 pi is also 1. So if k is an integer, any integer, from negative infinity to positive infinity, what is e to the j k 2 pi? It's 1. Also note that e to the j pi, with a magnitude of 1 and a phase of pi, has a value of negative 1. E to the j 3 pi, it just takes an extra loop around that, is also 1. So what is e to the j k pi? Again, k is an integer, any integer, from negative infinity to positive infinity. If k is odd, we get negative 1. If k is even, we get a positive 1. So this reduces to negative 1 to the k. You'll find places where you will need these. Write these on your note sheet. They're useful to keep in mind for simplifying your algebra.